Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Before we begin, take a moment to settle in wherever you are. Let your body sink into comfort, releasing whatever tensions the day has left behind. There's nowhere you need to be, nothing you need to accomplish, just gentle exploration ahead. Where in the world are you right now? A quiet room where you can finally let your mind rest? A peaceful space where the day's noise has faded? Wherever you are, you're exactly where you need to be. Tonight we're going to explore a question that seems to contain a contradiction. Can the universe be infinite and still have an end? We'll discover that infinity is stranger than we imagine, that endings come in different forms, and that something can extend forever in space while still facing ultimate transformation in time. The answer reveals deep truths about existence, eternity, and the nature of finality itself. But don't worry. This isn't going to be an overwhelming journey through abstract paradoxes or a dizzying plunge into mathematical impossibilities. Instead, we'll move slowly and thoughtfully through the concepts, building understanding piece by piece, finding clarity where confusion seemed inevitable. By the end, I think you'll have a richer appreciation not just for how infinity and endings can coexist, but for what this tells us about the universe's ultimate fate. If you enjoy these calm explorations of cosmic paradoxes and ultimate questions, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being part of this community of curious minds, so settle in now. Let your shoulders drop, releasing tension you didn't know you were carrying. Take a slow, deep breath in, feeling your lungs expand, and release it gently. Feel yourself sinking deeper into comfort with each exhale, and let's begin our slow drift through infinity and endings, exploring how something endless can still finish, how forever can include finality. There's nowhere you need to be, no boundaries you must cross. Just listen, and let the paradoxes unfold like space itself, extending without limit yet heading toward transformation. To understand whether the universe can be infinite and still have an end, we must first clarify what we mean by infinite and what we mean by end. Infinity is one of mathematics' most counterintuitive concepts. It's not a number, but rather a concept of endlessness, of quantity or extent without bound. In everyday language, we use infinity loosely to mean very large or countless. But mathematical infinity is more precise and more strange. The simplest infinity is counting forever. 1, 2, 3, continuing without stopping. The natural numbers are infinite because there's always one more. This countable infinity has a specific size in mathematics, called a left null. All countably infinite sets have this same cardinality despite seeming different. But there are larger infinities. The real numbers between 0 and 1 are uncountably infinite, a larger infinity than the natural numbers. This was Georg Cantor's revolutionary discovery in the late 1800s. Infinity comes in different sizes, and some infinities are genuinely larger than others. For physical space, infinity means extent without boundary. If space is infinite, travelling in any direction never reaches an edge because no edge exists. This spatial infinity is what we mean when asking if the universe is infinite. Does space extend forever? Or does it have finite volume? These different notions of ending are crucial for understanding how infinity and endings might coexist. The question in our title contains an apparent paradox. If something is infinite, extending forever, how can it end? Infinity suggests eternal continuation. End suggests termination. They seem logically opposed, mutually exclusive concepts. But the paradox resolves when we recognize that infinity and eternity are not the same thing. And endings come in different forms. Space can be infinite while time remains finite. The universe might extend infinitely far but exist for finite duration. Or space and time might both be infinite. Yet the universe still reaches an end state beyond which no interesting changes occur. This would be ending not as termination, but as reaching asymptotic final condition, The universe continues existing, but in unchanging equilibrium. Another possibility involves infinite space fragmenting. Different regions could reach different end states, even while space overall remains infinite. The heat-death scenario provides clear example of how infinity and ending coexist. Space extends forever. But all activity eventually ceases. In heat death, the universe reaches maximum entropy. Energy becomes uniformly distributed. Temperature approaches absolute zero everywhere. No stars shine, no planets orbit, no structures exist. Just cold, dilute gas spreading through infinite space forever. This is an end in the sense that everything we associate with a living universe is finished. Yet space and time continue infinitely. The universe becomes a frozen, unchanging expanse, infinite in extent, eternal in duration, but ended in any meaningful sense. This illustrates how endings need not mean annihilation. They can mean transformation to final unchanging state. Another way infinity and endings relate involves infinite time with discrete events. Infinite duration doesn't mean things happen forever. Imagine a universe where events occur at intervals that double each time. First event at 1 second, next at 2 seconds, next at 4 seconds. This sequence completes in finite time, specifically at 2 seconds, even though infinitely many events occur. The series converges. Similarly, the universe might complete infinitely many processes in finite time through similar convergent sequences. Infinity describes spatial or temporal extent. Endings describe states or processes. They can coexist without logical contradiction. The universe could be infinite spatially, extending forever in all directions, yet still face ultimate ending temporally. Or it could be infinite temporally, existing forever, yet reach end state where nothing meaningful changes. Or it could be finite in some senses and infinite in others, with endings applying to the finite aspects. Understanding this requires careful thought about what we mean by universe, by infinite, and by end. The universe might refer to all of space, which could be infinite, or it might refer to the observable universe, which is definitely finite, or it might refer to the matter and energy within space, which could be finite even if space itself is infinite. Infinite might mean spatial extent, temporal duration, matter quantity, or possible states. Each type of infinity relates differently to endings. End might mean cessation of existence, reaching final state, completing all processes, or transforming beyond recognition. With these clarifications, we can explore how modern cosmology addresses the question of whether the universe can be infinite and still end. The answer is nuanced and depends on which infinities and which endings we're considering. But fundamentally, yes, infinity and endings coexist. One of the clearest ways the universe can be infinite and still have an end involves the distinction between space and time. Space might extend infinitely in all directions, having no boundary or edge. Yet the universe could still have finite temporal extent. If time began at the Big Bang 13.8 billion years ago, the universe has finite age even if space is infinite. This means infinite space can coexist with bounded time. Space goes on forever, but time had a beginning and might have an end. The future ending could involve time itself stopping, though this seems physically problematic within general relativity. This demonstrates how infinity in space and time doesn't prevent ending. The ending is transformation to eternal stasis. Another scenario involves the Big Rip. If dark energy strengthens over time, expansion accelerates without bound. Eventually, expansion becomes so rapid that it tears apart galaxies, then solar systems, then planets, then atoms themselves. This could occur in finite time, perhaps 20 billion years. Space is infinite, but structures end abruptly through violent disruption. After the Big Rip, space continues expanding infinitely. Time continues flowing, but all structure has been destroyed. Again, we have spatial and temporal infinity coexisting with ending. The ending is catastrophic destruction rather than gradual decay. A third possibility involves vacuum decay. Our universe might occupy a metastable vacuum state that could decay to lower energy. If vacuum decay occurs, a bubble of true vacuum forms and expands at light speed, transforming everything it encounters. Inside the bubble, physics is different. Particles have different masses. Chemistry doesn't work the same way. From our perspective, this is absolute ending. Our universe is replaced by something radically different. But space overall remains infinite. Regions outside the bubble continue in our physics. The decay bubble expands forever, but never encompasses infinite space. This creates an interesting scenario where parts of infinite universe end while other parts continue indefinitely. Different regions could undergo decay at different times, creating patchwork of different physics across infinite space. These scenarios show that spatial infinity doesn't prevent endings. Infinite space can host finite duration processes. The distinction between space and time is crucial. Infinity in one doesn't require infinity in meaningful behavior in the other. General relativity treats space and time as unified space-time, but they play different roles in cosmic evolution. Space provides stage for events. Time provides dimension, along which change occurs. They're connected but distinct. Infinite spatial stage can host drama with definite ending. The stage persists, but the performance concludes. This analogy helps clarify how infinity and endings coexist. The theatre is boundless, but the play finishes. Mathematically, infinite three-dimensional space at each moment is compatible with finite or infinite temporal duration. An infinite temporal duration is compatible with universe, reaching final state where time continues but nothing changes. The confusion arises from conflating different types of infinity and different notions of ending. This is the most likely fate given current understanding. Infinite spatial extent, infinite temporal duration, yet definite ending. The ending is not destruction but transformation to maximum entropy state, where time loses meaning and space becomes uniform. We'll explore this in more detail later, but for now, we established that spatial infinity and temporal ending are perfectly compatible. Another way infinity and endings coexist involves infinite time combined with processes that asymptotically approach final states. Even if time extends infinitely forward, the universe can still end in the sense of reaching a state from which it never meaningfully changes. This asymptotic ending is mathematically and physically well defined. It's the limit that processes approach without ever quite reaching. In mathematics, sequences can approach limits, 1/2, 3/4, 7/8, approaching one but never arriving in finite steps. After 10 to the 100 years, the universe is very close to heat death. After 10 to the 1,000 years, even closer. The distance from final state decreases without bound. In this sense, the ending is reached asymptotically. This notion of asymptotic ending is crucial for understanding how infinite time can include finality. The universe never stops existing. Time never ceases. But meaningful change ceases asymptotically. Another example involves exponential decay. Radioactive atoms decay with characteristic half-lives. After many half-lives, almost all have decayed. Mathematically, complete decay requires infinite time, but practically after enough time, the difference from complete decay is negligible. The universe's evolution is similar. Many processes decay exponentially. Star formation declines exponentially. Structure dissolution occurs exponentially. These processes are asymptotically complete. In finite time, they're nearly done. In infinite time, they're exactly done. The asymptotic ending is a genuine ending even though it's approached gradually over infinite duration. This resolves another apparent paradox. If time is infinite, doesn't that mean things continue happening forever? Not necessarily. Things can continue happening but with decreasing frequency and significance. asymptotically approaching zero activity. In heat death, rare quantum fluctuations might occasionally create temporary structure, but averaged over time, nothing happens. These fluctuations don't prevent heat death from being an ending. They're infinitesimal blips in overwhelming stasis. The measure of activity approaches zero asymptotically. The ending is statistical rather than absolute, but is no less real. Time dilation provides another perspective on asymptotic endings. Near black hole event horizons, time slows dramatically. From an outside observer's perspective, nothing ever quite crosses the horizon. It approaches asymptotically. Yet we don't say the infalling matter doesn't reach the horizon. It reaches in the matter's proper time, and that's what matters. Similarly, the universe reaches heat death in cosmic time even if the approach is asymptotic from certain perspectives. The key insight is that asymptotic limits are genuine destinations, not merely approached but never reached. In infinite time, what is approached asymptotically is achieved. The limit state is the final state. This makes asymptotic endings philosophically satisfying. The universe completes its evolution even though the process takes forever. There's no moment when heat death suddenly begins. Instead, the universe smoothly transitions, always becoming more like heat death. Eventually, the difference between current state and heat death becomes arbitrarily small. This is completion of evolution. Mathematically, we use limit notation. As time approaches infinity, entropy approaches maximum. Temperature approaches zero. These limits are the ending states. They characterize the universe's fate despite being reached asymptotically. But the principle remains. Infinite time permits asymptotic endings that are genuine conclusions to cosmic evolution. Understanding this resolves much confusion about infinity and endings. They're not opposed, but describe different aspects of temporal evolution. Infinity describes duration. Asymptotic ending describes final state. Both can be true simultaneously. The universe can exist forever while still finishing its journey through state-space, arriving at final destination. This is perhaps the most common scenario in contemporary cosmology. Infinite time, infinite space. Yet definite ending. The heat death of the universe represents the most studied example of how infinity and endings coexist in cosmology. Heat death is the state of maximum entropy, where energy is uniformly distributed and no gradients exist to drive processes. This concept emerged in the 19th century from thermodynamics. The second law states that entropy always increases in closed systems. If the universe is a closed system, its entropy continually increases. Eventually, entropy reaches maximum possible value. At maximum entropy, no further change occurs because all configurations are equally probable and randomly distributed. This is heat death. Not cessation of existence, but transformation to featureless equilibrium persisting forever. Black holes dominate for a time, but even they evaporate through Hawking radiation. A solar mass black hole evaporates in 10 to the 67 years. Supermassive black holes last longer, perhaps 10 to the 100 years, but eventually all black holes evaporate. After black hole evaporation, only dilute photons and occasional particles remain, separated by vast distances. These particles continue spreading apart as space expands. Density and temperature approach zero asymptotically. Eventually, the universe is cold and empty beyond imagination. Average photon wavelengths stretch to cosmic horizon scales. Particles are so dispersed that interactions between them essentially never occur. The universe becomes profoundly inactive. This is heat death in expanding universe. Not thermal equilibrium at high temperature, but approach to absolute zero in infinite expansion. It's still maximum entropy because at such low density and temperature, all accessible states are equally occupied. Time continues flowing, space continues expanding, but nothing interesting happens. The universe has ended functionally. The timeline for heat death is staggering. Star formation ceases after about 100 trillion years when gas is exhausted. White dwarf and neutron star cooling takes 10 to the 32 years. Black hole evaporation extends to 10 to the 100 years. Beyond that, proton decay might occur if protons are unstable, taking 10 to the 40 years for significant numbers to decay. After all these processes complete, the universe is in deep heat death. Yet infinite time remains. What happens in infinite time after heat death? Mostly nothing. The universe sits in maximum entropy state. Occasionally quantum fluctuations might create temporary order. A rare fluctuation might spontaneously assemble a few atoms. Given infinite time, such fluctuations eventually occur anywhere in space. But they're infinitesimally rare. This leads to strange scenarios like Boltzmann brains, conscious observers formed by random fluctuation. In infinite time and space, anything allowed by physics eventually occurs through quantum fluctuation, no matter how improbable, but averaged over time and space. Heat death persists. Fluctuations are negligible blips in overwhelming stasis. Heat death is thus an ending compatible with infinite space and infinite time. The universe continues but as unchanging expanse. Philosophically, this is bleak. Everything we value, all complexity and structure, is temporary against heat death's eternity. Yet heat death is not certain. It depends on dark energy remaining constant and proton stability and other assumptions. If dark energy evolves, different fates are possible. If protons are completely stable, heat death has slightly different character. If vacuum decay occurs, heat death might be interrupted by transformation to different physics. But given current observations and standard physics, heat death is most likely ultimate fate. This makes heat death paradigmatic example of infinite universe with definite ending. Infinite space, infinite time, yet certain transformation to final inactive state. Infinity and ending coexisting perfectly. Understanding heat death helps grasp how endings work in infinite contexts. They're not terminations, but asymptotic convergences. The universe approaches heat death smoothly, continuously, inevitably. The ending is gradual but certain. This is ending not as catastrophe but as fading. The cosmos grows old, cold and quiet, extending forever in all directions. To fully understand how the universe can be infinite and still end, we must appreciate that infinity comes in different varieties. Mathematics distinguishes between countable and uncountable infinities. But physical infinity has its own important distinctions. Spatial infinity means extent without boundary. If you travel in any direction forever, you never reach an edge because none exists. This doesn't necessarily mean space is homogeneous. Infinite space could contain infinite stars and galaxies distributed throughout, or it could be empty beyond certain regions. Infinity describes extent, not content. Temporal infinity means duration without end. Time continues forward forever, with no final moment. Again, this doesn't specify what happens in time, only that time keeps flowing. These two infinities, spatial and temporal, are independent. Space can be infinite with finite time, or vice versa, or both, or neither. Phase space includes all possible configurations of matter and energy. For quantum systems, this is infinite dimensional Hilbert space. The universe as physical object might be finite, but the mathematical description requires infinite dimensional structures. These different infinities interact in complex ways with notions of ending. Spatial infinity allows asymptotic endings, where different regions reach final states independently. Temporal infinity allows asymptotic convergence to final states over infinite duration. Phase space infinity allows the universe to explore infinitely many configurations before settling into final state. Another important distinction is between bounded and unbounded infinity. Mathematically, sets can be infinite yet bounded. The interval from 0 to 1 contains infinitely many real numbers, yet is bounded between 0 and 1. Could the universe be infinite yet bounded somehow? This seems contradictory, but careful thought reveals possibilities. In time, bounded future infinity would mean infinitely many events occurring in finite duration, convergent series summed to finite values, a sequence of events at 1 second. 1/2 second later, 1/4 second later completes in 2 seconds despite infinite events. Could the universe's entire future history complete in finite time through similar convergence? Some eternal inflation models suggest something like this. Infinite events occur across multiverse, but local time remains finite. If both space and time are infinite but energy becomes uniformly distributed, then heat death occurs despite infinities. The key is recognizing that infinity and finitude, infinity and endings, can mix in various ways. Not everything about the universe need be infinite for it to count as infinite in meaningful sense. And not everything must end for the universe to have an ending in meaningful sense. These nuances are essential for mature understanding of cosmic fate in light of possible infinities. Modern cosmology embraces these subtleties, describing universe's future in careful terms that avoid oversimplification. The universe can be infinite in multiple ways while still facing definite transformation to final state. This isn't paradox, but sophisticated recognition of how infinity operates in physical contexts. The second law of thermodynamics is fundamental to understanding how infinite universes can have endings, as it governs the flow of cosmic evolution. The second law states that entropy, a measure of disorder or randomness, always increases in closed systems over time. This might seem like obscure technical principle, but it has profound implications for the universe's fate. Entropy increase is why coffee cools, why rooms get messy, why processes are irreversible. It's the arrow of time. The second law guarantees this evolution. Entropy increase is not just probable but certain, following from statistical mechanics. At microscopic level, entropy relates to number of possible arrangements of particles consistent with macroscopic properties. High entropy means many microscopic possibilities. Low entropy means few possibilities, requiring special organized configuration. The universe started in low entropy state at Big Bang. Why this was so remains profound mystery, but given low entropy start, entropy must increase. The universe evolves from special organized state toward generic disordered state. This evolution is heat death. The ending is not imposed externally but follows inevitably from entropy increase. Can entropy increase continue forever? In infinite time, doesn't entropy eventually saturate at maximum? Yes, that's precisely the heat death state. Entropy reaches maximum and remains there forever afterward. This is asymptotic ending. Entropy approaches maximum symptotically, effectively reaching it in infinite time. Once at maximum entropy, no further entropy increase is possible. The system is in equilibrium. Time continues, but entropy remains constant. The second law is satisfied, and nothing changes. This is how thermodynamics produces endings in infinite contexts. Entropy curves define trajectories through state space. These trajectories converge to maximum entropy point. Once there, evolution ceases even as time continues. The second law thus provides mechanism for ending compatible with infinities. It's not about space or time running out, it's about entropy saturating, energy spreading thin, gradients disappearing. These processes have definite endpoints. Those endpoints are reached asymptotically in infinite time, or approximately in very long finite time. Either way, the second law drives universe toward final state recognizable as ending. Challenges to this picture exist. Does second law apply to universe as whole? Is universe truly closed system? If multiverse exists, maybe our bubble universe isn't closed. Entropy could be transferred to other bubbles, or quantum gravity effects might modify thermodynamics at extreme scales. These possibilities remain speculative. For now, standard thermodynamics provides best understanding of cosmic fate. and standard thermodynamics clearly predicts heat death regardless of spatial or temporal infinities. The second law makes endings inevitable through entropy's relentless increase toward maximum. Energy dissipation plays a crucial role in how infinite universe can have ending, as usable energy becomes progressively less available. Thermodynamics distinguishes between energy and useful energy. Total energy is conserved, but useful energy dissipates. Useful energy is free energy, capable of doing work. Heat in cold environment has low useful energy, despite containing energy. As processes occur, free energy converts to heat. Entropy increases while total energy remains constant. Eventually all free energy is exhausted. Only heat remains uniformly distributed. No work can be extracted. This is another way to characterize heat death, not as lacking energy, but as lacking useful energy. Black holes evaporate through Hawking radiation, converting their mass energy into thermal radiation over vast timescales. Each energy dissipation process moves universe closer to maximum entropy and heat death. In infinite space, these processes occur everywhere. Each region follows similar trajectory toward energy exhaustion. There's no center losing energy to periphery. Every region loses its energy to expanding space around it. The expansion itself contributes to energy dissipation. As space grows, photon wavelengths stretch, losing energy to redshift. This cosmological redshift drains energy from radiation, cooling the universe even without interactions. Dark energy complicates this picture. Dark energy density remains constant as space expands, creating energy seemingly from nothing. But dark energy is not useful energy. It cannot be extracted or converted to other forms. It drives expansion but does nothing else. So even with dark energy, useful energy still dissipates. The universe's expansion ensures this dissipation continues inexorably. Eventually, useful energy density becomes arbitrarily small. Nothing remains to power processes or maintain structures. This happens throughout infinite space. No region is spared. Energy dissipation is a universal consequence of expansion and thermodynamics. The ending isn't that energy disappears. Energy is conserved. The ending is that energy becomes useless. In physics terms, free energy approaches zero even as total energy remains constant. This distinction is subtle but crucial. Heat death is not energy death but free energy death. The universe retains energy but in form that cannot drive change. It's energetically dead, though not energetically absent. In infinite space, this creates a strange situation. Infinite total energy exists, but zero useful energy remains. Energy density approaches zero. Temperature approaches zero, yet integrated over infinite volume. Total energy could be infinite. But even infinite total energy doesn't prevent ending if it's uniformly distributed at negligible density. No gradients mean no flows. No flows mean no processes. No processes mean effective ending. This shows how infinity and ending coexist through energy dissipation. Extent is infinite, but activity approaches zero. The universe becomes increasingly empty of activity, even as it remains infinite in space and time. Understanding energy dissipation clarifies heat death's mechanism. It's not catastrophic destruction, but gradual exhaustion. Stars flicker out, black holes evaporate, radiation cools, everything winds down smoothly over vast time spans. The ending is more whimper than bang, more fading than termination. But it's ending nonetheless, and this ending occurs regardless of spatial infinity. Energy dissipation works the same in finite and infinite spaces. Each region can exhaust its useful energy independently. Together they constitute universal ending. The universe's expansion plays a critical role in how infinite cosmos can have ending, as expansion drives isolation and energy dissipation. Current observations show the universe is expanding, with distant galaxies receding from us proportionally to their distance. This expansion is space itself growing. Galaxies aren't moving through space, but being carried by expanding space. The expansion rate is measured by the Hubble constant, currently about 70 kilometers per second per megaparsec. After about 100 billion years, assuming continued acceleration, only gravitationally bound local group is observable. All other galaxies have receded beyond horizon. The night sky becomes profoundly empty except for local group members. This isolation is one form of ending. The rich visible universe ends, replaced by cosmic loneliness. But isolation also affects energy flow. Regions beyond horizon cannot exchange energy or information with us. They're causally disconnected. Each horizon volume becomes isolated island, evolving independently. This fragmentation of infinite universe into isolated patches is crucial for understanding heat death in infinite space. Each patch reaches its own local equilibrium independently. Collectively, these constitute universe-wide heat death. There's no coordination needed. Each region follows second law locally. Together they produce global heat death. The expansion-driven isolation makes this possible. Without isolation, energy might flow between regions, complicating entropy increase. But with isolation, each region is effectively closed system. Thermodynamics applies cleanly to each. The ending in each region is guaranteed by second law. Collectively, infinite universe ends through innumerable local endings. Expansion also contributes directly to entropy increase through cosmological redshift. As photons travel through expanding space, their wavelengths stretch. Energy decreases while number of photons stays constant. This redshift increases entropy. The photon gas becomes cooler and higher entropy as expansion continues. Eventually, photon wavelengths stretch to cosmic horizon scales. Their energy becomes negligible. Universe cools asymptotically. This cooling is universal. Every region experiences it. Together, they cool toward absolute zero. The combination of acceleration, isolation, and redshift drives universe toward cold, dark, empty future. Each local region becomes isolated from neighbors, exhausts its energy, and cools toward zero temperature. This is ending through expansion and isolation. The universe fragments into uncommunicating patches, each reaching heat death. From inside any patch, the universe appears to end as everything beyond horizon disappears and local energy exhausts. From God's eye view, infinite universe continues forever, but as collection of isolated dead regions. This is how expansion enables ending in infinite universe. It breaks global structure into local patches with local endings. The expansion timeline matters. Acceleration began relatively recently, about 5 billion years ago. Before that, expansion was decelerating. Distant regions were accessible, at least in principle. But acceleration sealed their fate. Once recession velocity exceeds light speed, regions are lost forever. The future involves increasing isolation. The observable universe shrinks in physical content even as space expands. This shrinking is another way to understand the ending. The rich interconnected cosmos ends, replaced by isolated fragments. Understanding expansion's role clarifies how infinity and ending coexist. Expansion drives system toward final state. That final state is heat death in isolated patches. Together, they constitute ended universe despite infinite extent. Black holes and their eventual evaporation through Hawking radiation provide another crucial element in understanding how infinite universe can end. Black holes form when massive stars collapse, or through other concentration processes. They represent ultimate gravitational traps. Nothing escapes from inside event horizon, not even light. Black holes grow by consuming matter and energy. In universe's late stages, black holes become dominant structures. Stars produce black holes. Galaxies merge, creating supermassive black holes. Eventually, black holes dominate the mass budget. Everything else either orbits black holes or has been consumed by them. One might think black holes are eternal, accumulating matter forever, growing without bound. But as the universe expands and cools, background temperature drops. Eventually, background becomes colder than even large black holes. Once this happens, black holes begin net evaporating. They lose mass faster than gaining from surroundings. The evaporation accelerates as holes shrink. Smaller mass means higher temperature means faster radiation. A solar mass black hole takes about 10 to the 67 years to evaporate completely through Hawking radiation. Supermassive black holes like those at galaxy centers take far longer, perhaps 10 to the 100 years. But eventually, all black holes evaporate. No black hole is immune. Here's only question of timescale. After all black holes evaporate, the universe contains only dilute radiation and occasional particles. This marks transition to deep heat death. Black holes were last concentrated energy stores. Their evaporation converts remaining concentrated energy into diffuse radiation spreading through space. The radiation from evaporation itself dissipates through expansion. Eventually, even this radiation cools to negligibility. What remains is universe at essentially zero temperature with essentially zero density. The process of black hole formation and evaporation is thus cycle that exhausts universe's energy stores. Stars create black holes from nuclear energy. Black holes concentrate gravitational energy. Hawking radiation disperses everything. This cycle concludes with maximum entropy. All concentrated energy has been transformed to diffuse heat. In infinite space, innumerable black holes form and evaporate. Each follows same trajectory toward evaporation. Collectively, they process universe's matter through formation and evaporation cycle. The timescale is vastly longer than universe's current age, but in infinite time, it completes. After perhaps 10 to the 100 years, all black holes have evaporated. Universe enters final heat death phase. This represents clear ending even in infinite universe. Black holes mark final chapter of active universe. Their evaporation is final major event in cosmic history. Afterward, essentially nothing happens. Black holes also raise interesting questions about information. If black holes evaporate, what happens to information they consumed? Information paradox has been a major puzzle in theoretical physics. Does information escape somehow, or is it destroyed? Recent work suggests information escapes through subtle correlations in Hawking radiation. Information is conserved, but for understanding cosmic fate, information's fate is secondary. The key point is black holes evaporate. This shows how specific physical processes lead to endings in infinite contexts. It's not abstract thermodynamics alone, but concrete mechanisms like Hawking radiation that drive toward heat death. These mechanisms operate identically in finite and infinite universes. Scale doesn't matter for basic physics, so black hole evaporation contributes to ending in both finite and infinite universes equivalently. Understanding the timescales involved in cosmic ending helps appreciate how processes complete despite infinity. The universe is currently 13.8 billion years old. This seems immensely long by human standards. But compared to timescales of cosmic ending, current age is infinitesimal. The universe is extraordinarily young. Star formation continues now. Stars shine. Galaxies interact. The cosmos remains vibrant and active. Proton decay, if it occurs, becomes relevant on timescales of 10 to the 40 years or longer. If protons decay, then even white dwarfs and neutron stars eventually disintegrate into lighter particles and radiation. This would occur after about 10 to the 40 years, leaving only black holes and diffuse particles. Black holes, as discussed, evaporate through Hawking radiation over incredibly long time scales. Stellar mass black holes take 10 to the 67 years. Supermassive black holes take up to 10 to the 100 years. After 10 to the 100 years, all black holes have evaporated. Universe contains only radiation and particles. This marks deep heat death. Beyond this point, Essentially nothing happens except rare quantum fluctuations. These timescales are difficult to comprehend. 10 to the 100 years is 1 Google years. A Google is 1 followed by 100 zeros. It's incomprehensibly vast compared to current universe's age. Yet it's finite. In infinite time, 10 to the 100 years passes. The process is complete. After this timescale, universe has effectively ended. No structures exist. No processes occur. Time continues flowing. Space continues expanding, but nothing changes in a meaningful way. This demonstrates how finite timescales lead to endings despite infinite time. The processes have definite durations. After those durations, they're complete. Infinite time afterward doesn't undo completion. The ending persists for remaining infinite duration. Another way to think about timescales is through half-lives and exponential decay. Many processes decay exponentially. Star formation declines exponentially. Structure dissolution occurs exponentially. Exponential processes have characteristic timescales. After several timescales, process is essentially complete. Even though mathematical completion requires infinite time, practical completion occurs in finite time. After 10 characteristic times, exponential process is more than 99.9% complete. The universe's evolution involves many exponential processes. Together they drive toward heat death on composite timescale. That timescale is dominated by longest process, black hole evaporation at 10 to the 100 years. After this, universe is effectively in heat death. Further evolution is negligible. These timescales show ending isn't instantaneous transition, but gradual evolution over vast durations. The universe ages slowly. Activity declines smoothly. The ending approaches asymptotically, but approaches steady. Each era transitions predictably to next as physical processes run their courses. Understanding timescales makes ending concrete rather than abstract. Specific numbers, even if incomprehensibly large, define the trajectory. We can calculate when stars stop forming, when black holes evaporate, when heat death is reached. These calculations give definite answers. The ending has schedule, even if schedule extends beyond human comprehension. This concreteness is important. It shows ending is real prediction of physics, not vague speculation. Given current understanding of particle physics, thermodynamics, and cosmology, these timescales follow necessarily. Unless new physics intervenes, these endings will occur on these timescales. The vastness of timescales doesn't make endings less real. It just emphasizes how young universe currently is. We exist in cosmic dawn. The long twilight and eventual night lie ahead over incomprehensible durations, but they will come. The ending is certain even if distant. While heat death is most likely ending given current observations, alternative scenarios exist where universe ends more dramatically, including the Big Rip. The Big Rip occurs if dark energy strengthens over time rather than remaining constant. If dark energy density increases, expansion accelerates faster and faster without bound. Eventually expansion becomes so rapid that it overwhelms all forces holding structures together. First, galaxy clusters are torn apart as expansion overcomes gravitational binding holding them together. Then individual galaxies dissolve as their stars are ripped away from each other by runaway expansion. Solar systems disintegrate as expansion overcomes gravitational attraction between stars and planets. Planets themselves are torn apart as expansion forces overwhelm molecular and atomic bonds. Finally, even atoms are ripped apart as expansion forces exceed electromagnetic forces binding electrons to nuclei. This catastrophic shredding of all structure is the Big Rip. It occurs in finite time if dark energy strengthens appropriately. The timeline depends on how rapidly dark energy grows. Some models predict Big Rip in 20 billion years, others predict longer timescales, perhaps hundreds of billions of years, but it's finite, not asymptotic. The Big Rip represents abrupt ending in contrast to heat death's gradual decline. Everything is violently destroyed in relatively brief period as expansion goes infinite in finite time. After Big Rip, no structures exist. Even particles might be shredded. Space continues existing and expanding but contains nothing organized. This is ending through catastrophic disruption rather than gradual exhaustion. From perspective of our question, Big Rip is interesting because it's compatible with spatial infinity. Space can be infinite yet still undergo Big Rip. Every region is ripped apart simultaneously as expansion diverges. The ending is global and sudden rather than local and gradual like heat death. However, current observations don't support Big Rip scenario. Dark energy appears consistent with cosmological constant, not strengthening field. Measurements of dark energy equation of state parameter suggest it's very close to -1, matching cosmological constant. If parameter is exactly -1, no Big Rip occurs. Only if parameter is less than -1 does Big Rip happen. Current constraints place parameter close to -1 with small uncertainty. Big Rip seems unlikely. But it remains possibility if dark energy evolves in ways not yet detected. Future observations might reveal strengthening. The Big Rip illustrates how infinity doesn't prevent endings. Even infinite space can be catastrophically disrupted. The key is that disruption is process occurring throughout space, not requiring space itself to end. Space persists post-Rip, but everything in space has been destroyed. This is ending of structures, not space. Understanding this distinction helps clarify how endings work. They don't require space or time to terminate. They require transformation to state where meaningful structures and processes no longer exist. Big Rip achieves this through violent disruption. Heat death achieves it through gradual dissipation. Both are endings compatible with infinite space and infinite time. The Big Rip also raises questions about what happens after. If space continues post-Rip, does anything reform? Quantum fluctuations might eventually create new particles. Over vast timescales, structure might re-emerge. But post-Rip evolution is highly speculative. We don't know if particles can exist stably in such extreme conditions. The Rip might be permanent ending with no recovery, or it might be transitioned to different regime. These uncertainties show limits of current understanding. Extreme scenarios push physics beyond tested domains. For now, Big Rip remains theoretical possibility more than likely outcome. But it serves as a reminder that endings can be sudden as well as gradual, violent as well as peaceful. The universe's fate depends on dark energy's nature, which remains incompletely understood. While heat death is most likely ending given current observations, alternative scenarios exist where universe ends more dramatically, including the Big Rip. The Big Rip occurs if dark energy strengthens over time rather than remaining constant. If dark energy density increases, expansion accelerates faster and faster without bound. Eventually, expansion becomes so rapid that it overwhelms all forces holding structures together. First, galaxy clusters are torn apart as expansion overcomes gravitational binding holding them together. Then individual galaxies dissolve as their stars are ripped away from each other by runaway expansion. Solar systems disintegrate as expansion overcomes gravitational attraction between stars and planets. Planets themselves are torn apart as expansion forces overwhelm molecular and atomic bonds. Finally, even atoms are ripped apart as expansion forces exceed electromagnetic forces binding electrons to nuclei. This catastrophic shredding of all structure is the Big Rip. It occurs in finite time if dark energy strengthens appropriately. The timeline depends on how rapidly dark energy grows. Some models predict Big Rip in 20 billion years. Others predict longer timescales, perhaps hundreds of billions of years, but it's finite, not asymptotic. The Big Rip represents abrupt ending in contrast to heat death's gradual decline. Everything is violently destroyed in relatively brief period as expansion goes infinite in finite time. After Big Rip, no structures exist. even particles might be shredded. Space continues existing and expanding but contains nothing organized. This is ending through catastrophic disruption rather than gradual exhaustion. From perspective of our question, Big Rip is interesting because it's compatible with spatial infinity. Space can be infinite yet still undergo Big Rip. Every region is ripped apart simultaneously as expansion diverges. The ending is global and sudden rather than local and gradual like heat death. However, current observations don't support Big Rip scenario. Dark energy appears consistent with cosmological constant, not strengthening field. Measurements of dark energy equation of state parameter suggest it's very close to -1, matching cosmological constant. If parameter is exactly -1, no Big Rip occurs. Only if parameter is less than -1 does Big Rip happen. Current constraints place parameter close to -1 with small uncertainty. Big Rip seems unlikely. But it remains possibility if dark energy evolves in ways not yet detected. Future observations might reveal strengthening. The Big Rip illustrates how infinity doesn't prevent endings. Even infinite space can be catastrophically disrupted. The key is that disruption is process occurring throughout space, not requiring space itself to end. Space persists post-rip, but everything in space has been destroyed. This is ending of structures, not space. Understanding this distinction helps clarify how endings work. They don't require space or time to terminate. They require transformation to state where meaningful structures and processes no longer exist. Big Rip achieves this through violent disruption. Heat death achieves it through gradual dissipation. Both are endings compatible with infinite space and infinite time. The Big Rip also raises questions about what happens after. If space continues post-rip, does anything reform? Quantum fluctuations might eventually create new particles. Over vast timescales, structure might re-emerge. But post-rip evolution is highly speculative. We don't know if particles can exist stably in such extreme conditions. The rip might be permanent ending with no recovery, or it might be transitioned to different regime. These uncertainties show limits of current understanding. Extreme scenarios push physics beyond tested domains. For now, Big Rip remains theoretical possibility more than likely outcome, but it serves as a reminder that endings can be sudden as well as gradual, violent as well as peaceful. The universe's fate depends on dark energy's nature, which remains incompletely understood. Another dramatic ending scenario involves vacuum decay, where the universe transitions to a lower energy state, with potentially catastrophic consequences. Quantum field theory suggests fields have vacuum states, their lowest energy configurations. Our universe might occupy a false vacuum, a metastable state that appears stable, but isn't the true lowest energy. If this is so, the universe could tunnel quantum mechanically from false vacuum to true vacuum. This tunneling would create a bubble of true vacuum that expands at light speed, converting everything it touches. Inside the bubble, physics is different. Particle masses change. Forces have different strengths. Chemistry doesn't work the same way. From our perspective, this is absolute ending. Our universe is replaced by something fundamentally different. The probability of vacuum decay depends on energy difference between false and true vacua, and the barrier height between them. If our vacuum is deeply metastable, decay might be so improbable that it won't occur for unimaginable durations. But if it's only marginally stable, decay could occur any time, even now. Measurements of Higgs boson mass suggest our vacuum is metastable. The standard model vacuum appears unstable at high energies. This means vacuum decay is possible, though tunneling rate is uncertain. If decay occurs, a bubble of true vacuum forms somewhere in space and expands at light speed. We wouldn't see it coming. No warning precedes the bubble wall's arrival. Our region would be instantly transformed. Everything we know would cease to exist, replaced by structures governed by different physics. This represents ending in most absolute sense. Not gradual decline, but instantaneous obliteration and replacement. Some physicists worry vacuum decay is imminent danger. Others think it's vanishingly unlikely. The truth is, we don't know vacuum stability precisely. Particle physics beyond standard model could stabilize or destabilize vacuum. Vacuum decay illustrates deep connection between particle physics and cosmology. The fate of infinite universe depends on quantum field properties at highest energies. These properties are largely unknown, making vacuum decay scenarios speculative but scientifically serious. Understanding vacuum decay requires better understanding of Higgs field and any physics beyond standard model. Future collider experiments and theoretical developments might clarify vacuum stability. For now, it remains another way infinite universe could end, though only partially in spatial sense. Vacuum decay is ending through transformation and replacement rather than dissipation or disruption. It shows variety of possible endings even in infinite contexts. The universe's ultimate fate might involve combination of scenarios: heat death in some regions, vacuum decay in others. Infinity allows diverse endings across different regions rather than single global fate. Although current observations suggest eternal expansion, alternative scenarios where universe recollapses remain theoretically important for understanding endings. If dark energy weakens over time, or if matter density is higher than measured, expansion could eventually reverse. Gravity would overcome expansion. The universe would begin contracting, galaxies approaching each other. This contraction phase leads to Big Crunch, opposite of Big Bang. As contraction proceeds, temperature rises. Galaxies collide and merge. Space shrinks. Eventually, everything crushes together into infinitely dense singularity, mirror image of Big Bang singularity. This represents total ending. Not just structures, but space and time themselves might cease at Big Crunch. Each cycle might last trillions of years, but infinite cycles extend infinitely into past and future. This provides different answer to our question. The universe is finite spatially, but infinite temporally. Yet it still has endings in sense that each cycle ends in contraction and bounce to next cycle. The current cycle will end. Its ending is not heat death, but collapse and transformation. However, current observations strongly disfavor Big Crunch. Dark energy drives acceleration, not deceleration. Unless dark energy reverses, which seems unlikely, universe won't recollapse. The measured spatial curvature is very close to zero, suggesting flat or slightly open geometry, not closed. Flat universe doesn't recollapse. It expands forever toward heat death. So Big Crunch appears ruled out by observations, but it remains valuable theoretical alternative. It illustrates how endings depend on cosmic geometry and dark energy properties. Different assumptions lead to radically different fates: eternal expansion versus ultimate collapse. The fact that observations determine which fate applies shows cosmology is empirical science. We don't merely philosophize about endings, we measure cosmic parameters and calculate which ending follows. This makes cosmological endings scientific predictions, not speculative scenarios. Big Crunch also illustrates another point. In this scenario, spatial and temporal infinities can trade off. Finite space allows Big Crunch ending. Infinite time through cycles allows eternal existence. The universe ends in each cycle, but persists eternally through infinite cycles. This shows flexibility in how infinity and endings relate. Multiple combinations are logically possible. Which combination describes reality depends on observational cosmology. For now, Big Crunch seems unlikely, but it remains conceptually important for understanding cosmic fates. It shows that endings can mean total annihilation of space and time, not just transformation to inert state. This is philosophically most extreme ending, though physically perhaps less bleak than eternal heat death. In Big Crunch, everything ends together definitively in heat death. Everything fades gradually forever. Which is more disturbing depends on perspective. Both represent ultimate cessation of familiar universe. The key insight is that both are endings compatible with certain assumptions about cosmic properties. Endings are real possibilities, not prevented by infinities, and their nature depends on physics. In infinite time after heat death. Quantum fluctuations introduce fascinating complications to the concept of ending. Quantum mechanics says vacuum isn't empty but seethes with quantum activity. Virtual particles constantly appear and disappear. These fluctuations are normally negligible at macroscopic scales, but in infinite time, even improbable events eventually occur. In heat-death state of maximum entropy, rare fluctuations might spontaneously create temporary order. A random fluctuation might assemble a few atoms. Given enough time, larger fluctuations might create complex structures. In infinite time, eventually fluctuations create any structure allowed by physics, no matter how improbable. This includes stars, planets, even living beings formed purely by random fluctuation from equilibrium. These Boltzmann brains are conscious observers created spontaneously by improbable fluctuation. The probability is astronomically low, perhaps 1 in 10 to the power 10 to the power 50 for each event. Understanding quantum fluctuations clarifies what we mean by ending in quantum universe. Absolute stasis is impossible due to quantum nature of reality. Everything fluctuates at some level, but fluctuations can be negligible, creating effective stasis that constitutes ending for practical purposes. This is yet another way infinity and ending coexist. Infinite time allows infinite fluctuations yet doesn't prevent effective ending. The ending is overwhelming statistical state, not perfectly rigid structure. Quantum considerations thus add nuance to heat death without fundamentally changing conclusion. The universe reaches maximum entropy state persisting forever, with rare, negligible fluctuations. This is ending in meaningful sense, even if not ending in absolute sense. The distinction between effective ending and absolute ending matters philosophically but not practically. For any observers, processes or structures we care about, heat death is absolute ending. Rare Boltzmann brains don't constitute continuation of cosmic history in a meaningful way, so we maintain that heat death is ending compatible with infinity, with quantum fluctuations as minor technical caveat. While cosmic endings lie in distant future, current observations provide strong constraints on which ending is most likely. The key observations involve measuring universe's expansion rate, matter density, and dark energy properties. Type Ia supernovae provide standardizable candles for measuring cosmic distances and expansion history. Observations in late 1990s showed distant supernovae were fainter than expected, implying accelerating expansion. This discovery revealed dark energy's existence and earned Nobel Prize in 2011. Further supernova observations have refined measurements. Expansion is definitely accelerating. The acceleration began relatively recently, about 5 billion years ago, when dark energy came to dominate matter density. Cosmic microwave background observations provide complementary constraints on cosmic geometry and composition. The CMB power spectrum encodes information about universe's spatial curvature and matter energy contents. Analysis of CMB data shows universe is spatially flat to high precision. Curvature parameter is consistent with 0. This flatness suggests universe is either infinite or extremely large. Small finite universes are ruled out. CMB observations also precisely measure dark energy density and equation of state parameter. Dark energy comprises about 68% of universe's total energy. Density. Matter is about 32%. The equation of state parameter W, relating pressure to density for dark energy, is measured to be very close to -1. Value of -1 corresponds to cosmological constant, unchanging vacuum energy. If W equals -1 exactly, dark energy never changes. Acceleration continues forever toward heat death. If W is slightly less than -1, dark energy strengthens. This could lead eventually to Big Rip. If W is slightly greater than -1, dark energy weakens. Far future might differ from cosmological constant prediction. Current measurements constrain W to be within few percent of -1. Best fit is consistent with exact -1. This supports cosmological constant interpretation and heat death fate. Baryon acoustic oscillations in galaxy clustering provide another measurement of expansion history. These oscillations are remnants of sound waves in early universe, creating characteristic scale in matter distribution. By measuring this scale at different distances, astronomers trace expansion history. Results are consistent with accelerating expansion driven by cosmological constant. Gravitational lensing observations also constrain dark energy. The growth rate of cosmic structure depends on dark energy properties. Strong gravitational lensing by galaxy clusters and weak lensing from large-scale structure both provide information. These observations generally support cosmological constant model, though some tensions exist between different measurements. The Hubble constant tension is notable discrepancy. Local measurements give higher value than CMB inferred value. This might indicate new physics or systematic errors. Resolution is active area of research. But the tension doesn't significantly affect conclusions about ultimate fate. Both values support eternal acceleration. Taken together, observations strongly favour a future of eternal accelerating expansion toward heat death. Big crunch is ruled out. Dark energy prevents recollapse. Big rip is unlikely unless W differs from -1 more than measurements suggest. Vacuum decay remains possible but unpredictable. No observations directly constrain it, so heat death emerges as most observationally supported fate. The universe will expand forever. Stars will exhaust fuel. Black holes will evaporate. Heat death will ensue. This is prediction of observational cosmology, not mere speculation. The timeline is uncertain in details, but overall trajectory is clear. Understanding observational basis for predictions grounds the discussion in empirical science. We're not philosophizing abstractly, but interpreting actual measurements of cosmic properties. This makes cosmic fate topic of scientific investigation, with predictions subject to observational tests. Future observations will refine understanding. Better measurements of dark energy equation of state might reveal evolution. Improved measurements of Higgs field properties might clarify vacuum stability. Gravitational wave observations might reveal new physics affecting cosmic fate. But unless observations radically change, heat death remains most likely ending. This observationally grounded prediction shapes contemporary thinking about cosmic endings and infinity. The universe can be infinite spatially and temporally while still facing definite ending through heat death. Observations confirm this isn't paradox but physical reality of our cosmos. The coexistence of infinity and endings in cosmology connects to ancient philosophical questions about eternity and finitude. Philosophers have long contemplated whether universe is eternal or had beginning, whether it will end or persist forever. Ancient Greek philosophers debated these questions. Aristotle argued for eternal universe without beginning or end. Others, including some Christian philosophers, argued for creation from nothing at definite moment in time. Modern cosmology shows both views capture partial truths. Universe had temporal beginning but might be spatially infinite. It will persist eternally into future, but will reach end state effectively concluding meaningful cosmic evolution. This nuanced picture requires updating philosophical frameworks developed before modern cosmology. The distinction between different types of infinity is crucial. Temporal eternity differs from spatial infinity. Eternity in philosophical sense often meant unchanging permanence rather than infinite temporal duration. Others argue meaning is local and temporal, not requiring cosmic permanence. Human meaning comes from our lives, relationships, choices. It doesn't need universe-scale persistence. The fact that universe ends doesn't diminish present significance. It contextualizes but doesn't negate meaning. This philosophical response treats meaning as emergent human phenomenon rather than cosmic property. We create meaning through our existence. Cosmic fate affects context, but not fundamental capacity for meaning. Another perspective comes from process philosophy. If reality is fundamentally process, endings are natural. Every process completes. The universe is cosmic scale process that also completes. There's no tragedy in completion, only natural conclusion of what had beginning. This process view sees endings as fulfillment rather than loss. The universe accomplishes its existence through its full temporal trajectory. Beginning, middle, and end together constitute complete cosmic story. Without ending, story would be incomplete, eternally unfinished. This reframes endings positively. They're necessary for completeness, not unfortunate limitations. Whether one finds this perspective satisfying depends on philosophical temperament. Some prefer eternal persistence without endings. Others accept temporality as essential to existence. Modern cosmology suggests the latter is more consistent with physical reality. The universe is temporal, historical entity with beginning and ending, not eternal unchanging structure. Understanding philosophical implications helps integrate scientific cosmology with broader questions about existence and meaning. Science tells us what will happen. Philosophy helps us understand what it means. Together they provide richer understanding than either alone. The coexistence of infinity and endings revealed by cosmology challenges simplistic philosophical categories. Reality is more subtle than either pure eternalism or pure finitism capture. Infinity and finitude, eternity and ending, mix in complex ways that require sophisticated philosophical analysis to appreciate fully. Understanding what endings mean philosophically and existentially helps appreciate how infinity and endings coexist conceptually. In everyday experience, endings are familiar. Stories end, lives end, projects complete. But cosmic endings seem different in scale and finality. They're not just one thing ending, but everything ending. Yet perhaps this difference is merely quantitative, not qualitative. Cosmic endings are endings like any others, just larger. The meaning we attach to endings shapes how we interpret them. Endings can mean loss, completion, transformation, or transition. Some argue yes. If everything ends in nothing, then nothing ultimately mattered. But this reasoning is questionable. Value exists in the present, in experiences and relationships as they occur. That they don't persist eternally doesn't retroactively eliminate their value when they existed. A beautiful sunset isn't less beautiful because it fades. A meaningful conversation isn't less meaningful because it ends. Temporality might be essential to value. If everything persisted unchangingly forever, would it retain significance? Perhaps endings create value by making existence precious and time meaningful. Without endings, nothing would be at stake. Every moment would be like every other, endlessly repeating. Endings create narrative structure. They give time direction and meaning. They make choices matter. From this perspective, cosmic endings aren't nihilistic but meaningful. They complete cosmic story. The universe has full existence from beginning through evolution to ending. This completeness has integrity. Whether one finds this satisfying depends on whether one values completion over persistence. Both perspectives are coherent. Neither is objectively correct. They reflect different value frameworks. Understanding endings' meaning requires engaging both factual questions about physics and value questions about significance. Science provides facts. Philosophy provides frameworks for interpreting significance. Together they help us grapple with implications of infinite universe that still ends. The eventual ending of infinite universe has profound implications for the long-term future of life and consciousness. If universe reaches heat death, no life can survive indefinitely. All biological processes will eventually cease. But the timeline is so vast that countless possibilities exist before that final state. Life might persist for trillions of years, spreading throughout galaxy and even to other galaxies if expansion allows. Advanced civilizations might develop technologies we can't currently imagine, extending existence far beyond biological constraints. But eventually, all energy sources exhaust. No technology can create energy from nothing. The second law of thermodynamics ensures that usable energy dwindles asymptotically towards zero. This creates hard physical limit on complexity and consciousness, regardless of technological advancement. Some physicists and futurists have explored whether consciousness could persist indefinitely through clever strategies. Freeman Dyson calculated that consciousness requires energy flow. As temperature drops in an expanding universe, energy requirements decrease. By slowing mental processes to match available energy, consciousness might persist arbitrarily long on finite energy. But this requires perfect efficiency and reversible computing, which might be impossible due to quantum and thermodynamic limits. Even with maximal efficiency, finite resources ultimately limit total thoughts or experiences. In truly infinite time after heat death, even most efficient consciousness exhausts its resources. So eternal consciousness seems impossible. Consciousness is a temporary phenomenon even in infinite universe. This conclusion is sobering. All consciousness in universe is transient against cosmic timescales. Yet this doesn't diminish consciousness's significance. Temporary doesn't mean meaningless. The experiences of conscious beings are real and valuable during their occurrence. That consciousness eventually ends doesn't retroactively eliminate its value. Another perspective involves information preservation. Even if consciousness ends, might information persist? In heat death, information is maximally scrambled. All records are erased. Nothing remains of cosmic history. This is information death as well as consciousness death. The universe forgets itself completely. From philosophical perspective, this raises questions about whether anything existed if no record remains. If all information is lost, did cosmic history really matter? Or does existence require being recorded somewhere? These questions verge on metaphysics. Science can't definitively answer whether unrecorded existence is meaningful, but intuitively, yes, existence matters even if unremembered. The experiences occurred. They were real at their time. That future contains no trace doesn't change past reality. Still, the total information erasure of heat death is philosophically disturbing. It's ending not just of processes but of memory. The universe loses all trace of its own history. Nothing remains to show it was ever different. For conscious beings contemplating this fate, it invites reflection on legacy and permanence. Nothing we create persists ultimately. All civilizations, all achievements, all knowledge eventually vanishes. This can inspire nihilism or acceptance. We create and achieve knowing it's temporary. The temporality might make creation more precious rather than less. We build knowing it won't last, and we build anyway. This existential courage in face of impermanence is a meaningful response to cosmic endings. Another consideration involves suffering. If consciousness ends, future suffering also ends. Some find this comforting. All pain eventually ceases. No one suffers eternally. Heat death is perfectly peaceful. Free from all suffering because free from all experience. Whether this is good or bad depends on whether one values existence despite suffering or sees ending suffering as positive outcome. Antinatalist philosophies might view cosmic ending positively. All potential suffering is eventually eliminated, but most people value existence and consciousness despite suffering. The ending is loss, not relief. These varied perspectives show no single correct emotional response to cosmic endings. Different value systems lead to different evaluations. Science provides facts, values provide significance. Understanding implications for life and consciousness helps ground abstract cosmology in concerns relevant to beings like us. We're part of cosmos facing these endings. Our own ultimate fate connects to cosmic fate. Though we won't personally experience heat death, Our species' long-term survival connects to cosmic constraints. If humanity or its descendants persist millions of years, they'll confront changing cosmic environment. They might migrate to younger stars, then to other galaxies, always moving to regions with available energy. Eventually, even this strategy exhausts. Energy sources are finite in local regions. The ending is certain, even if distant. This certainty shapes long-term thinking about civilization's future. Understanding cosmic endings provides context for thinking about humanity's significance and potential. We're temporary phenomena in temporary universe. This shared temporality connects human to cosmic. The fact that universe can be infinite yet have ending connects to fine-tuning questions about why universe has properties permitting observers. Fine-tuning refers to apparent special tuning of physical constants and initial conditions enabling complexity and life. If constants were slightly different, stars wouldn't form, chemistry wouldn't work, or universe would recollapse quickly. The range permitting life appears narrow. This seems remarkable and demanding explanation. Or perhaps we're early in cosmic history. Later observers in older universes might find very different apparent dark energy effects. The fine-tuning question connects to endings, because endings depend sensitively on these tuned parameters. Small changes in dark energy equation of state would produce big rip or big crunch rather than heat death. Small changes in vacuum stability would make vacuum decay likely rather than unlikely. So which ending occurs depends on finely tuned parameters whose values seem special. This raises question of why universe has these particular values producing eternal expansion toward heat death. Is there deeper principle determining these values? Or are they random selections from multiverse possibilities? These questions remain unsolved. Fine-tuning is recognized problem without consensus resolution. For our purposes, fine-tuning shows that infinity and endings relate through cosmic parameters. The values determining spatial infinity, temporal infinity, and ending type are interconnected. We can't understand endings without understanding why constants have their observed values. If multiverse exists, different regions might have different fates. Some expand eternally, others crunch, others rip. Our region has eternal expansion fate because constants happen to have those values here. Other regions with different constants have different fates. Infinity allows this diversity. In infinite multiverse, all possible endings occur in different regions. This makes endings observer-relative in extended sense. Different observers in different regions experience different cosmic fates. From God's eye view, spanning entire multiverse, no single ending exists. Different regions end different ways. But from any observer's perspective, their region has definite fate determined by local constants. Fine-tuning thus connects to endings through anthropic reasoning in multiverse context. We observe constants producing eternal expansion because those constants permit observers like us. The ending we predict is the ending compatible with conditions necessary for our observation. Whether this explanation is satisfying depends on whether one accepts multiverse framework. Without multiverse, fine-tuning remains puzzling. Why these particular values? With multiverse, fine-tuning is explained anthropically. These values occur somewhere, and we're there because we must be. But multiverse itself requires explanation. Why does multiverse exist? Why does it have structure producing varied constants? These meta-questions show fine-tuning is deep problem not fully resolved by any current framework. For understanding infinity and endings, fine-tuning reveals how cosmic parameters determine ultimate fate. The universe's ending type isn't arbitrary, but follows from tuned parameters we observe. Understanding those parameters is key to confident predictions about endings. Current observations support heat death because they measure parameters consistent with eternal accelerating expansion. But uncertainties remain. Better measurements might reveal evolution in dark energy or instability in vacuum. Such discoveries would change predicted ending dramatically. Fine-tuning thus reminds us that cosmic predictions depend on measured parameters and our theoretical understanding of them. While current best understanding predicts heat death, we must remain open to surprises as understanding improves. Coming to terms with universe's ending, despite its infinite extent, requires philosophical and psychological adjustment. Modern cosmology's predictions aren't comforting. The universe ends not heroically, but through gradual decay into eternal darkness. This knowledge can provoke various emotional and philosophical responses. For all human purposes, universe is effectively eternal. No one experiences or confronts the ending. So cosmic endings are intellectually interesting but practically irrelevant to daily life. This allows compartmentalizing cosmic knowledge. We acknowledge heat death intellectually while living as though universe is permanent. This isn't denial but appropriate response to timescales beyond human relevance. Some find solace in contributing to something larger than themselves, even if temporary. Working toward human flourishing, scientific understanding, or artistic creation has meaning through connection to shared human project. That project ultimately ends doesn't diminish current participation's significance. We're part of cosmic story in our brief moment. Playing our part well has meaning independent of story's ending. Religious perspectives vary. Some traditions emphasize eternal spiritual existence transcending cosmic fate. If consciousness or soul transcends physical universe, cosmic endings don't eliminate meaning. But this requires accepting religious frameworks science cannot evaluate. For those seeking meaning within naturalistic framework, accepting cosmic endings is more challenging but possible. Meaning is created phenomenon, not discovered property. We make meaning through choices and values. Cosmic endings don't prevent meaning making. They simply contextualize it within larger trajectory. Psychological adjustment to cosmic endings might involve several stages like grief, denial, anger, bargaining, depression, acceptance. Some initially reject cosmological predictions. Others feel anger at unjust fate. Some try to find loopholes, scenarios where endings might be avoided. Some experience depression at meaninglessness of existence given inevitable ending. Finally, acceptance arrives. The universe ends. This is reality. We live and create meaning anyway. This acceptance isn't resignation, but mature acknowledgement of reality combined with commitment to meaning despite impermanence. Its philosophical stance recognizing both cosmic endings and human capacity for meaning-making. Many find this acceptance liberating. Releasing attachment to permanence allows fuller engagement with present. If nothing lasts forever, we might as well enjoy and create now. Finding meaning in experience rather than legacy. This present-focused approach to meaning emphasizes quality of experience over duration of effects. We live well not to achieve eternal legacy, but to live well in itself. Cosmic endings become irrelevant to this immediate meaning-making. Whether one finds these philosophical responses satisfying depends on personal temperament and values, but collectively they represent serious attempts to find meaning despite cosmic endings. Understanding and accepting endings is part of mature relationship with cosmological knowledge. We know universe's fate. We integrate this knowledge. We find meaning anyway. This integration of cosmic knowledge with human values represents philosophical achievement of modern cosmology. We can know dark truths about reality while maintaining meaning and purpose in our lives. The universe can be infinite and still end, and we can know this while still finding life meaningful. After exploring theoretical possibilities, it's important to assess what we can actually know about universe's ultimate fate with current physics. Cosmology is empirical science. Predictions about endings rest on observations and tested theories. But predicting far future involves extrapolating current understanding over unimaginable timescales. Many uncertainties exist. Physics beyond standard model might change predictions dramatically. Dark energy's nature remains incompletely understood. It might be cosmological constant or evolving field. Current observations strongly support cosmological constant, but precision is limited. If dark energy evolves even slightly, predictions about expansion rate and ultimate fate change significantly. Better measurements of dark energy equation of state might reveal time dependence that changes predicted ending. Vacuum stability is another major uncertainty. Current measurements suggest metastability, but with large uncertainties. Better understanding of Higgs field and physics beyond standard model might clarify whether vacuum decay is likely. If vacuum is actually stable, heat death proceeds uninterrupted. If unstable, decay might intervene. Proton stability also affects predictions. If protons decay, matter dissolves faster than if protons are stable. Current experiments place lower limits on proton lifetime exceeding 10 to the 34th years. But whether protons decay at all remains unknown. Grand unified theories predict decay. Standard model doesn't include it. Future experiments might detect proton decay or push limits much higher. Quantum gravity effects at extreme scales might modify predictions in ways we can't currently calculate. If space or time becomes discrete at Planck scale, cosmological evolution at ultra-long times might differ from current predictions. These uncertainties mean predictions about ultimate fate are conditional on current understanding being correct. We predict heat death given cosmological constant, stable vacuum, and negligible quantum gravity effects. If any assumption proves wrong, predictions change. This isn't weakness but honesty about science's limits. We make best predictions with available information. As understanding improves, predictions refine. This is how science progresses. What we can say confidently is that endings are real physical predictions, not metaphysical speculation. Given current physics, universe faces definite end state within certain timescale ranges. The specific ending type depends on parameters we're measuring with increasing precision. Heat death is most likely given current data, but other scenarios remain possible. Observational cosmology continues improving measurements. Future observations will narrow uncertainties. Space missions like Euclid and Roman telescope will measure dark energy properties more precisely. Improved particle physics experiments might reveal beyond standard model physics affecting vacuum stability. Gravitational wave astronomy might detect signals revealing new physics at extreme energies. These observations will either strengthen confidence in heat death prediction or reveal need to revise understanding. Either outcome is scientific progress, either confirms or refines current models. For now, we acknowledge both what we know and what we don't know. We know universe is expanding, probably forever. We know dark energy dominates and drives acceleration. We know thermodynamics predicts entropy increase toward maximum. These facts make heat death most plausible ending given current understanding. But we don't know dark energy's precise nature or evolution. We don't know vacuum stability definitively. We don't know whether protons decay. We don't have complete quantum gravity theory. These unknowns leave room for surprises. Cosmic fate might differ from predictions. This uncertainty is appropriate. Extraordinary claims require extraordinary evidence. Predicting universe's fate over Google years is an extraordinary claim. Current evidence supports it but doesn't make it certain. Maintaining appropriate epistemic humility about cosmic predictions is important. We should be confident in well-supported conclusions while remaining open to revisions as understanding improves. The question of whether universe can be infinite and end is answered affirmatively with current knowledge. Infinity and endings coexist in multiple ways through spatial extent, temporal duration, and thermodynamic evolution. But details of how endings occur depend on physics we're still learning. Future discoveries might refine or revise predictions while likely maintaining basic conclusion that endings occur. Understanding what we know and what remains uncertain helps frame cosmic knowledge appropriately. We've learned remarkable amount about universe's past and probable future through observation and theory. This represents stunning achievement of human intellect and scientific method. Yet mysteries remain. The Universe hasn't revealed all its secrets, perhaps never will. Some aspects might be permanently beyond observation or understanding, but remarkable progress has occurred. Questions once purely philosophical now have scientific answers. Whether universe is infinite, whether it ends, what that ending looks like. These are now scientific questions with observational and theoretical bases. This progress grounds our understanding while maintaining openness to future discoveries. Beyond pure knowledge, understanding cosmic endings has value for how we think about existence, time, and meaning. Knowing universe's ultimate fate contextualizes human existence within larger cosmic narrative. We're temporary beings in temporary phase of cosmic evolution. This is our context. Understanding this context affects how we think about ourselves and our activities. It can provoke humility. Our concerns are cosmically insignificant. The universe doesn't care about human affairs. This humility can be healthy, combating ego and self-importance with perspective on actual scale. But understanding endings can also inspire appreciation. If everything is temporary, we might value present moment more fully. Knowing stars will die might make current starlight more precious. Impermanence creates value through scarcity. This aesthetic appreciation of temporality enriches experience. Endings make moments meaningful rather than meaningless. Understanding endings also affects how we think about time and change. If universe reaches heat death when nothing changes, time becomes meaningless in functional sense. This suggests time is deeply connected to change. Time exists because things change. When change ceases, time continues mathematically but loses significance. This insight clarifies time's nature as emergent from change rather than fundamental background. Philosophical discussions of time's nature benefit from cosmic perspectives. Understanding endings also provides perspective on human timescales and concerns. Our worries occupy years or decades. Cosmic processes span billions or trillions of years. Recognizing this gap can reduce anxiety about ephemeral concerns while maintaining engagement with present. We live in present while knowing present is brief moment in vast cosmic timeline. This temporal perspective is philosophically valuable even if practically not always easy to maintain. Understanding endings also raises questions about legacy and impact. If heat death erases everything, does legacy matter? Do achievements have lasting significance? One response is that legacy is a short-term phenomenon. We affect coming generations, and that's enough. Our actions ripple through causal chains affecting future people. This provides significance independent of eternal persistence. We contribute to ongoing human story even though story eventually ends. Another response is that striving for impact matters psychologically regardless of ultimate futility. We find meaning in trying to make difference, even knowing difference isn't permanent. The effort itself has value as expression of care and commitment. Understanding endings thus doesn't eliminate motivation but contextualizes it. We act knowing actions are temporary but meaningful in their moment and limited ripple effects. Cosmological knowledge also affects spiritual and religious perspectives. Some religious frameworks promise eternal existence transcending cosmic endings. Cosmology can't verify these claims but can describe physical universe's fate. Reconciling religious beliefs with cosmological knowledge requires sophisticated theology. Some embrace both, seeing spiritual transcendence as separate from physical cosmos. Others find cosmology challenging to religious views and must choose between or synthesize them. These personal philosophical journeys vary. Cosmology provides information. Individuals interpret significance. For secular worldviews, cosmological endings are more directly challenging. Without transcendent realm, cosmic endings are final endings. No escape or consolation exists. Facing this reality requires courage and philosophical maturity, but many find it empowering rather than depressing. Reality is what it is. We accept and engage fully. This courageous acceptance characterizes mature secular response to cosmic knowledge. Understanding endings also contributes to scientific literacy and cultural knowledge. An educated person should know basic facts about universe, including its likely fate. This knowledge is part of being informed citizen of modern technological society. Cosmology tells fundamental story about existence. Everyone should know this story's broad outlines. Teaching cosmology, including endings, serves educational function beyond pure knowledge. It develops critical thinking, statistical reasoning, and comfort with uncertainty. Students learn to evaluate evidence, understand theoretical frameworks, and accept provisional conclusions. These skills transfer to other domains. Cosmology education thus has practical value beyond specific content. Finally, understanding endings reveals human intellectual achievement. That we can predict universe's fate trillions of years hence based on current observations is remarkable. The scientific method's power to reveal such distant truths demonstrates its effectiveness. This should inspire confidence in science as a way of understanding reality. Appreciating scientific achievement requires understanding scope of knowledge gained. Cosmological predictions about endings represent pinnacle of human understanding of nature. Recognizing this value encourages supporting science and valuing knowledge for its own sake. The mathematical treatment of infinity and endings provides rigorous framework for understanding how they coexist. Mathematics has developed sophisticated tools for handling infinite processes and asymptotic behaviors. These mathematical concepts clarify physical cosmology's predictions about infinite universes' endings. Infinite series provide basic example. Series like 1/2 plus 1/4 plus 1/8 approaches finite limit of 1. This shows how infinite process can complete in sense of converging to definite value. Cosmological evolution resembles convergent series. Infinite time approaches definite final state. The mathematical limit characterizes state approached asymptotically as time goes to infinity. Measure theory provides framework for discussing infinite sets while avoiding paradoxes. When dealing with infinite space, measure theory specifies how to assign sizes or probabilities properly. This allows meaningful statements about properties of infinite universe. For example, we can say entropy density approaches zero almost everywhere in infinite space during heat death. Almost everywhere is measure theoretic term meaning except on set of measure zero. This precision clarifies what heat death means in infinite space. It's not that every single point has zero activity. Rather, regions with activity become negligibly rare measured appropriately. Topology provides another mathematical tool. Infinite spaces can have different topological properties affecting their structure. Whether space is open, closed or flat topologically determines global properties, like potential for finite volume. These topological considerations affect which endings are possible. Closed topology allows big crunch. Flat or open topology requires eternal expansion. Current observations support flat topology, ruling out big crunch. Dynamical systems theory studies how systems evolve over time, particularly long-term asymptotic behavior. Cosmology can be treated as dynamical system evolving through state space. Fixed points in state space represent equilibrium states where evolution ceases. Heat death corresponds to fixed point representing maximum entropy. The universe's trajectory through state space converges to this fixed point asymptotically. Understanding this as dynamical system clarifies mechanics of how ending approaches. Ergodic theory studies systems' long-term statistical properties. Ergodic systems explore all accessible states given infinite time. If universe is ergodic, it eventually reaches all states compatible with conservation laws. Heat death represents most probable state, the one with most microstates. Ergodicity explains why universe inevitably approaches heat death if given infinite time. Information theory quantifies entropy mathematically through Shannon or von Neumann entropy measures. These measures rigorously define entropy increase and maximum entropy states. Cosmological entropy can be calculated using these frameworks, making predictions precise. The second law becomes mathematical theorem in information theoretic framework. All these mathematical tools contribute to understanding infinity and endings rigorously. They show apparent paradoxes dissolve when treated carefully with appropriate mathematics. Infinity and endings don't contradict when properly formalized through limits, measures, and asymptotics. Mathematics also reveals subtleties. Different types of infinity require different treatments. Countable versus uncountable infinity matters for set theory but less for physical applications. Potential versus actual infinity affects philosophical interpretation but not physical predictions. These mathematical distinctions clarify thinking about infinite universes' properties. Mathematics doesn't just describe cosmology, it provides conceptual frameworks making sense of physical predictions. Without mathematics, notions like infinite space approaching maximum entropy would be hopelessly vague. Mathematics makes them precise, calculable, testable. This demonstrates mathematics' indispensability for modern physics. Physical intuition alone can't handle these concepts. Mathematical rigor is necessary for thinking clearly about infinities and endings. Understanding mathematical foundations deepens appreciation of cosmological predictions. We're not just speculating, we're calculating using well-established mathematical frameworks. These calculations yield definite predictions about cosmic fate. The predictions might be wrong if physics changes, but they're not vague or ambiguous given current physics. Mathematics ensures precision and clarity in discussing inherently difficult concepts like infinity and asymptotic endings. This precision distinguishes modern cosmology from ancient philosophical speculation. We have quantitative predictions, not just qualitative ideas. This makes cosmology scientific rather than merely philosophical. Mathematics enables this transformation from philosophy to science. One striking realization from understanding cosmic endings is that we exist extraordinarily early in universe's timeline. The universe is 13.8 billion years old, but it will exist for trillions of years before reaching heat death. We exist in first tiny fraction of cosmic history. The universe is profoundly young from ultimate perspective. This temporal positioning has interesting implications for our observations and expectations. We see vibrant universe full of stars, galaxies, and ongoing activity because we exist when these things are happening. Future observers, if any exist trillions of years from now, will see vastly different universe. They'll observe darkness as stars have died, isolation as galaxies have receded, and cold as temperature has dropped. Their cosmology would be almost impossible. No CMB to observe, no distant galaxies to study. They might not even realize universe had different past. Evidence would be gone. We're fortunate to exist when evidence of cosmic history is abundant and accessible. This is anthropic observation. Observers naturally exist when conditions permit observation. When universe becomes too cold and dark, no observers exist. We necessarily observe earlier vibrant phase, but it's still striking how early we are. Complex life might exist for trillions of years more. Why do we exist so early in the window of possibility? This question connects to habitability over time. Earth-like planets around Sun-like stars dominate early. Later, long-lived red dwarfs might host planets for trillions of years. Perhaps most observers exist later around red dwarfs. We're early anomalies, or perhaps life requires certain conditions more common in young universe. Galaxy mergers and star formation rates affect planet formation and element abundances. These might make early universe more conducive to life despite seeming less mature. Anthropic reasoning can't definitively answer these questions. We observe what we observe. But recognizing we're early in cosmic timeline provides perspective on our situation. We exist in cosmic springtime. Summer stretches ahead for trillions of years, but autumn and winter will eventually come as heat death approaches. Our moment is brief flourishing in long cosmic story. This realization can inspire both humility and appreciation. Humility because our time is tiny fraction of total. Appreciation because we exist during interesting epoch. We see universe full of structure and activity. This won't last forever. Understanding our temporal position also affects thinking about extraterrestrial intelligence. If intelligent life is rare, perhaps we're among first civilizations to arise, or perhaps many exist now, but most intelligent beings will exist in far future around red dwarfs. The Fermi paradox, asking where everyone is, might be partly answered by timing. If we're early, we wouldn't expect to see evidence of earlier civilizations because there weren't many. Future intelligence might be far more abundant than current intelligence. This speculative reasoning shows how cosmic timelines affect thinking about life's distribution. Living in cosmos's youth also means witnessing unique phases. Current epoch of galaxy formation and vigorous star formation won't repeat. Once gas is exhausted and stars die, that phase of cosmic history closes. We're observing universe during its most active, interesting period. This makes our observations scientifically valuable. Later observers couldn't make same observations. Cosmological knowledge we're gaining now might be inaccessible to future civilizations. This provides motivation for preserving knowledge. Future beings might benefit from our records, though preservation for trillions of years presents enormous challenges. Understanding temporal context also affects how we think about cosmic future. From our vantage point, heat death is incomprehensibly distant, but for universe itself, its inevitable destination not so far ahead. Our early position makes ending seem distant, but they're certain components of cosmic story. This perspective encourages thinking about ultimate questions even though they don't affect present. We're intellectually curious beings contemplating full cosmic narrative, not just our local moment. This cosmic perspective is part of what makes us human. We think beyond immediate concerns. Understanding we live in cosmos's youth contextualizes this perspective. We're early observers of much longer story. Our observations and thoughts are early chapters. This is simultaneously humbling and elevating. We're small in time and space, yet capable of comprehending vastness. As we conclude our exploration, we return to the central paradox. How can the universe be infinite and still have an end? We've seen this isn't truly paradoxical, but reflects subtleties in how infinity and endings relate. Infinity describes extent, spatial reach, or temporal duration. Endings describe states, transformations, or conclusions. These are different aspects of reality. They can coexist without contradiction. Spatial infinity means space continues forever without boundary. This is compatible with temporal endings. Time can flow forever, while universe reaches final unchanging state, infinite duration, definite ending. Or space can be finite while time is infinite through cyclic processes. Finite extent, infinite duration. Or both space and time can be infinite while processes conclude and activity ceases. The key insight is that endings don't require annihilation or termination of existence. They can mean transformation to final state, completion of processes, or approach to asymptotic limits. Heat death is ending as asymptotic approach to maximum entropy. Universe continues, but unchangingly. Big Rip is ending as catastrophic transformation. Structure is destroyed, but space persists. Vacuum decay is ending as replacement. Our universe is superseded, but space and time continue. Big Crunch would be ending as convergence, possibly cyclically repeating. Each type of ending coexists with various types of infinity in specific ways. Understanding requires clear thinking about what we mean by universe, infinite, and end. Vague language creates apparent paradoxes. Precise language reveals consistent pictures. The universe can be infinite in space yet finite in meaningful activity. It can be eternal in time yet finite in structural complexity. It can be bounded in some aspects while unbounded in others. Reality is more subtle than simple categories of finite versus infinite, ending versus eternal. Modern cosmology has revealed this subtlety through observations and theoretical frameworks. We've moved beyond philosophical speculation to scientific understanding of cosmic fate. The progress is remarkable. Questions that seemed purely metaphysical now have observational answers. Whether universe is infinite spatially depends on curvature, measurable through CMB observations. Whether it expands eternally depends on dark energy, measurable through supernova observations and other tests. What ending it faces depends on these measurements plus theoretical understanding of thermodynamics and quantum physics. This transformation of ancient questions into scientific ones represents triumph of human intellect and scientific method. We can know cosmic fate with increasing confidence through observation and reason. Uncertainties remain. Parameters aren't measured perfectly. Theories might need revision. But framework exists for answering questions and making predictions testable in principle. Embracing the paradox means accepting that reality operates by rules more sophisticated than everyday intuition. Infinity and endings coexist because they describe different dimensions of existence. We must think carefully, define terms precisely, and follow logic rigorously. When we do, apparent contradictions resolve into consistent understanding. The universe can be infinite and still end. This isn't magic or mystery once properly understood. It's consequence of how thermodynamics works, how expansion operates, how time flows. Physical laws permit and predict this coexistence. Mathematics describes it rigorously. Observations confirm current phase and constrain future evolution. Embracing this knowledge enriches understanding of existence and our place in cosmos. We live in infinite universe heading toward definite ending. This is our context. We're temporary structures in temporary active phase of cosmic evolution. Eventually activity ceases and heat death prevails, but that's trillions of years away. For now, universe is vibrant, structured, full of possibility. We exist in this special time, capable of understanding cosmic story including its ending. This capability is itself remarkable. We're universe contemplating itself, including its fate. This self-awareness distinguishes us. We know cosmic story and our place in it. Embracing the paradox means accepting this knowledge and finding meaning within it. The universe is infinite yet ending. We are temporary yet meaningful. Both truths coexist. Understanding their coexistence is philosophical achievement. It requires sophisticated thinking about infinity, endings, and existence. But the effort rewards with deeper appreciation of reality's nature. We understand more fully what it means to exist, to be part of cosmos, to face ultimate questions. This understanding is valuable for its own sake, regardless of practical applications. It represents human intellect at its best, grappling with deepest questions and finding answers. The question of whether universe can be infinite and still end is answered. Yes, and here's how. This answer satisfies intellectually while inspiring continued wonder at cosmic mysteries. We've learned much. More remains to learn. The journey continues. Thank you for journeying with me through this exploration of infinity and endings, this patient investigation of how the cosmos can stretch forever, yet still face finality. I hope you found peace in understanding that paradoxes dissolve with careful thought, that infinity and endings are not opposites but different aspects of reality, and that our temporary existence in infinite cosmos remains meaningful. Can the universe be infinite and still have an end? Yes. Space can extend forever while time approaches final state. Processes can conclude while existence persists. Activity can cease while space and time continue. Heat death awaits in trillions of years, infinite space approaching maximum entropy, infinite time flowing into unchanging stasis. Yet definite ending of all complexity and structure. The universe will be infinite yet ended, eternal yet finished, existing yet inactive. Wherever you are now, I hope you're ready for deep rest. Your breathing has found its gentle rhythm. Your mind has released the need for absolute answers to paradoxical questions. The mysteries we've explored perhaps help you feel both small in infinite space and significant in your capacity to comprehend cosmic fate. Sleep well tonight, knowing you exist in a universe that is simultaneously infinite in extent and finite in meaningful activity, that will last forever yet still reach its ending, that continues eternally yet completes its story. Dream peacefully of space without boundaries, yet time with destination, of asymptotic approaches to final states, of heat-death in infinite expanse. Dream of entropy increasing toward maximum, of stars dying and black holes evaporating, of universe growing cold and dark yet persisting eternally. Dream of infinity and endings dancing together, neither contradicting the other, both describing one vast cosmic reality. Good night. May your sleep be undisturbed and restorative. May tomorrow find you refreshed and renewed. And may you carry forward an appreciation for subtle truths, an understanding that reality transcends simple categories, and peace with infinity and endings coexisting. Can the universe be infinite and still have an end? Yes. Infinity describes extent. Endings describe states. They coexist perfectly in our remarkable cosmos. Space extends forever. Time flows eternally. Yet everything transforms toward final unchanging state. This is our universe. Infinite. Eternal. And ultimately ending. Understanding this paradox that isn't paradox is understanding reality's deep structure. Good night.